On to problem number 2. In problem number 2, it says that we are provided with a sample of ice, and that ice has a mass of 112 grams, and it has a temperature of minus 21.5 degrees Celsius. And the problem asks us to compute the amount of energy required to completely convert the ice into the vapor phase. And it asks us to provide our answer in units of kilojoules, where 1 kilojoule is equal to 1,000 joules. It also provides us with the specific and latent heat values that we need for this calculation below. So we have a value of the specific heat for ice, and we are given the value of 2.06 in units of joules per gram degrees Celsius, a value of the specific heat for liquid water, and the value that we are given is 4.16, again in units of joules per gram degrees Celsius. We're given a latent heat of fusion, and the value is 334 joules per gram. And finally, we're given a latent heat of vaporization that has a value of 2,261 joules per gram. So let's draw a diagram first. So on our figure here, on the y-axis, I'm going to record the temperature. And on the x-axis, we're going to record the cumulative energy that we input to our sample. This is just like we did in our Properties of Water lab. So we start off, and we're given an initial temperature of minus 21.5 degrees Celsius. And there's going to be a first regime of temperature increase, and I'll describe what these are in more detail in a moment. And I'm going to label this first area region 1. And then there's going to be a period in which the temperature is constant, and I'm going to label that region 2. And then there's a region of constant increase in temperature of our sample from 0 degrees C to 100 degrees C. And I'm going to label that region 3. And then there's going to be a period where we're at a constant temperature of 100 degrees C. And I'm going to label this region 4. And our final point, as the problem says, is the point at which our sample, which is initially ice, is completely evaporated. So let's label these regions. So region 1 is going to be used to denote the energy that is required to raise our sample from its initial temperature of minus 21.5 degrees Celsius to 0 degrees Celsius, or the melting or freezing point of water. Region 2 is going to represent the energy required to completely melt that sample. At a constant temperature of 0 degrees C. Region 3 is going to represent the amount of energy required to raise our sample from a temperature of 0 degrees C to 100 degrees C. So at this point, our sample is completely liquid, and we want to raise the temperature from 0 degrees C to 100 degrees C, which is the boiling point. And finally, region 4 represents the amount of energy required to completely evaporate our sample. Okay, so first we're going to write the two equations that we're going to need for these calculations. The first equation is going to be for regions 1 and 3, and it represents the amount of energy required to raise our sample over a given range of temperature. So it's going to be the mass, m, times c, the specific heat, times delta T, the change in temperature. The second equation is going to be the amount of energy required to either completely melt or completely vaporize our sample. So the easiest way to do this is to create just a table of calculations for each one of our regions. So we're going to have a calculation for region 1, and we're going to use this equation right here. And if we plug the numbers in, we have 112 grams in our sample. We're using the specific heat for ice, 2.06 joules per grams degrees Celsius. And we're raising our sample from minus 21.5 degrees Celsius to 0 degrees Celsius. Okay, so doing the units, we get a value of 4,960 joules. Okay, so let's proceed to region 2. So here we're going to use the other equation where we input the mass as 112 grams and we use the latent heat of fusion, which is given to us as 334 joules per gram. And again, the grams here cancel, and when we do the calculation, we should get a value of 37,408 joules. So on to region 3. We're again going to use that first equation up above, and when we input the numbers, again, our mass is still 112 grams. Our specific heat for liquid water is 4.16 joules per gram degrees Celsius. And we're raising our sample from 0 degrees C to 100 C. So our delta T is 100 C. When we cancel the units out, we get units of joules. And when we turn the numerical crank, we get 46,592 joules. Finally, for region 4, we're going to use the second equation up here. And again, the mass is still 112 grams of water. And we're using the latent heat of vaporization, which is 2,261 joules per gram. And when we turn the crank, we get 253,232 joules. So the total amount required to completely vaporize our sample is then just the sum of the energy required for each one of these regions. So all we do is sum up the total figure, which gives us a value of 342,192 joules for the total energy. Now the problem asks us to give the answer in units of kilojoules, and this is an energy unit conversion. And we recognize that, as the name implies, in 1 kilojoule, there are 1,000 joules. So the joules cancel out. We divide here by 1,000. And the final value we get is 342.2 kilojoules. And that's our answer.